Let's now try a second example of this type of time-dependent behavior, but an example where we have much richer phenomena, actually. We've got all the tools in place now, but let's look at something a little bit more complicated. So this will be example 2, and the general topic is what's called scattering theory, because we're sending a particle in, and it's interacting with some system represented by my potential, and now I'm seeing which way the particles go. So in the second example, it's going to build a lot on the first example. Let's just suppose we have pretty much the same example, but let's suppose the potential V naught is now actually less than 0. If I look at the situation then, what I would have is the potential of x versus x. I will have my incoming packet that's coming in with some energy value E, and the potential will again be 0 in this region, here in region 1. But now in region 2, instead of being a positive upward step in potential, we are going to make it a downward negative step in potential, like so. And this distance will be V naught, but remember V naught is now a negative number. Now, you know how we're going to set up this problem, right? Now there is going to be a K1 for this region, because this region is classically allowed, and we will have the same formula that we always have, right? It's for oscillatory regions, it's 2m over h bar squared times the energy minus the potential V of x. But in this case, the potential is 0. So we have the same exact result that we had previously. K2 now will be, again, of exactly the same formula. We have a K2 now, not an alpha 2, because this is classically allowed. And the formula will be, again, 2m over h bar squared times E minus V naught. Now remember, V naught has now turned into a negative number, which means this will actually be a larger energy now. And so, which seems to make some intuitive sense, I will have a larger K2 and therefore a larger momentum. Because after all, this represents something like a ball rolling down a hill. We expect it to pick up extra kinetic energy and extra momentum on side 2. Now, you further know, I think, exactly how we are going to go about solving this problem, right? We are going to write down for our solution time of the time independent Schrodinger equation, psi of x, right? Will look something like the following. We will have our solutions in the two different regions. In the first region, we will again do this, A1 cosine K1x plus B1 sine K1x. That proved to be very convenient, actually, for solving for the coefficients of alpha 1, of A1 and B1. And we will, for solving for the boundary conditions at x equals 0, just like we had before. Now, when we go into region 2, we also have these oscillatory solutions, and there's an alternate form that is going to be a little more convenient for us to write down the solution, following what we had seen as quite successful when we had done the upward potential step. What I'd like to do is to write down the solution here in terms of exponential solutions. So we will use that other form of the complex exponential. So there'll be a C1 e to the I K1x, and then there will be a D1 e to the minus I K1x as our general solution. Now I want you to recall that last time we had something very similar to this. We had C1 e to the minus, this is K2, I'm sorry, because that's region 2, of course. And this is for x less than 0, and this is for x greater than or equal to 0. Last time we had a C1 e to the minus alpha 2x plus a D1 e to the plus alpha 2x. Just reminding you of that. Now, last time we started with that as our general solution, But by arguing about boundary conditions, we were able actually to eliminate the possibility of this term using boundary condition number 3, that psi at plus or minus infinity cannot approach plus or minus infinite values itself. It had to stay normalized. There is actually, for this problem, a similar type, it's different, but a similar type of new, for us, boundary condition that applies that allows us to logically eliminate one or the other of these two terms. And if you give that a little thought, I think you'll begin to see what that term actually is. One of these two terms is a little bit suspicious when we begin to think about what they represent. I mean, after all, let's think a little about what we expect the before and after situation to be with this potential step. So before the collision, right, what we expect the wave function to look like is more or less what you're seeing here. I've got a packet that's coming in. Afterwards, right, if I had a pure classical particle, I would just roll down this step and keep going with a higher velocity. So what I would expect then would be that there would be some packet that continues along as what we would call a transmitted packet. But we also, if we're tuned to our wave physics, expecting something else. Because after all, I have a sudden change in the potential. That represents a sudden change in the propagation properties of my wave. And it's a general feature of wave behavior that whenever there is a sudden change in the propagation medium, such as when I go from a light beam going from air to glass, I get not only a transmission, but I also get a reflection back again. So I'm expecting I should get, I don't normally see it in classical physics, but in quantum mechanics where I have this underlying wave behavior, I would expect probably I will get a reflection also. So this is what I'm expecting to see at long times afterwards, and what I'm expecting to see here at long times before. If I now think about what this represents, it's kind of unusual, right? The first term represents, in the x greater than 0 region, a forward traveling or transmitted wave. So this term clearly represents this piece. This term, though, would represent a packet that exists here on the right-hand side for x greater than 0, but it exists here and it's traveling in a backward direction. Now, if we play the movie of this backwards, that would mean at very long negative times, this thing must have originated far out here, and it must therefore originate far out here and be traveling toward my region. But that would represent a very strange initial condition, right? An initial condition where I've got an incoming packet on the left and an incoming packet on the right. That would mean my initial condition is where I don't know if my particle is starting out on the left or right. There's probability for either case, but I somehow arrange so that there is this probability on the far left and on the far right end of finding my particle, and these probabilities are moving slowly toward the origin. That's an interesting starting condition. It's just not the type of, we could maybe set that up, but it's not actually the type of starting condition that we have in mind. It's not the experiment that we are trying to analyze. So we have a new type of boundary condition that we can use to eliminate this backward traveling term. And that's my fourth type of boundary condition. So I'm going to call that boundary condition number 4. And that's another one of our important lessons from this analysis. There's no apostrophe in that kind of lessons. And this is boundary condition number 4. And these generically are called a certain type of scattering boundary condition. These are generally called the forward or sometimes the outward scattering boundary conditions. And the idea, right, is that what we have only, right, is packets that I send something in, and then what I get is just things that are moving outward from the scatterer, not this extra strange inward, leftward moving piece. Now that's sort of their generic term. Because we are in one dimension, there actually are two types of these scattering boundary conditions. The first one is the type that we are looking at. This is called a left, and by left, just to remind myself, I'm coming in from the left. So a left incident, right? That's what I mean. I'm coming in from the left, a left incident boundary condition. That's the case we're talking about here. And what it says is that I can't have any backward, or in this case, right, leftward moving wave on the right. So that would mean no leftward, which would be this direction, right? Leftward moving wave on the far right. There's also then, of course, a right incident boundary condition where I'm sending my particles in then from the right. And what it says is then that there is no rightward, which would mean moving this way, moving wave on the far left. Think about it, right? If I were to be having a boundary condition where I'm sending someone in from this side towards my step, which I certainly could do, right? I have this right incident boundary condition. I'm coming in from the right, but there shouldn't then be some rightward moving packet that was coming in from the far left. So depending on which case you want to analyze, which direction you want to send your particles in for your scattering calculation, you would use one or the other of these boundary conditions. So I want to put a box around this. This is our fourth and almost final type of boundary condition. The final type is what happens when a wave function hits a delta function. You will have a chance to look at that later on in the course. Okay, great. So now I want to think a little bit about what we will be doing next to come to the final solution. If you think it through, it's going to be very similar to what we have been doing, right? I will now, this C1 then will ultimately just determine the scale, right, or the normalization of my wave function. I will then match slope and value at the origin and then solve for A and B in terms of this overall scale. And then finally, so that I can analyze things, I'm going to rewrite my sine and my cosine in terms of forward and backward traveling waves, and I'm going to produce a solution that looks a lot like the solution that we had derived before. And in fact, if you think about it, all of the algebra I'm about to do will be exactly the same, right? The only difference in this algebra, I called it A1 and B1. There's the cosine and the sine. There's the C1, right? The only difference in the algebra that I'm about to do is that now, every time where in the past I had a minus alpha 2, now I will see a plus ik2. Right? It's going to be exactly the same thing. So I can actually immediately write down the solution in this form, right? Just making that one replacement where I replace all minus alpha 2s with ik1s. So let's just write that down. So to find, it's going to be, or put it this way, it's going to be same solution as before. There's a very powerful technique underlying this. This is why I'm emphasizing it. Same solution as before, except replace minus alpha 2 with ik2. Now, it turns out, actually, we can tidy this up a little bit. There's a more compact way of writing this. Notice I could just multiply both sides of this by I, so I'd be replacing minus I alpha 2, or, I'm just saying the same thing. I could replace minus I alpha 2 with I times ik2, but I times ik2, two i's gives me a minus k2. And, well, then that's the same thing, of course. I've got a minus sign on both sides. So everywhere where I see an I alpha 2, I can just replace it with a plus K2 and immediately write down my solution. Now, I don't want you to think that this was just some kind of accident that this worked out so conveniently. There's a very powerful idea underlying this, something called analytic continuation. And that is just the more general, powerful idea that, well, look, this is exactly the same problem as before. It's just that V0 now is a negative number. So I should have just immediately taken my previous solution and just made V0 negative and then taken everything over from there. Now, at first, that might seem a little scary if you look at some of our algebra, right? Because if I replace V0 with a negative number, that would make Q0 squared a negative number, which at first sounds like you can't do it. But of course, we're very familiar with complex numbers. That would just mean that Q has become imaginary. But there's nothing wrong with that, right? Q could become an imaginary number for us. No problem, right? The beauty of complex arithmetic is that the answers hold because all the rules we're applying do exactly the same thing, whether the quantities are real numbers or imaginary numbers or complex numbers. It doesn't matter. The algebra is exactly the same. So we could have just taken this solution and just used our alpha 2, right, evaluating the thing as a complex number. So let's see if that actually works for the analytic continuation idea. So the analytic continuation, again, is it's okay to use previous solution extended. That's where the continuation idea comes from. Previous solution extended to where quantities become imaginary. Quantities become imaginary or complex. So, for example, right, we know what that previous solution looks like. It's written up above. The only tricky part would be this alpha 2. So alpha 2, if you look at it, right, it was defined as the square root of 2m over h bar squared times v0 minus e. That was its mathematical definition. Now, there's nothing wrong with the fact that if v0 is negative now, this becomes an imaginary number, right? That's the whole idea here. So let's rewrite it, though, as a positive number and try to relate it to K2, because this looks a lot like the formula for K2. In fact, the formula for K2 is exactly the same thing, except E and V are written in a backwards order. But I can accomplish that. That would just be rewriting alpha 2 as minus 1 times 2m over h bar squared times e minus v0. And if I continue with my arithmetic, I can factor out the square root of minus 1, which is I, but we have to be a little careful. Square root of minus 1, we don't know necessarily which sign to take. It would be plus or minus I. We will come back to which sign is appropriate. And then I have this square root of the remaining pieces, which is precisely the definition of K2. So what this is saying is I could have taken my previous solution, which had the e to the minus alpha 2x, right, and just use the fact that alpha 2 actually mathematically is equal to plus or minus ik2. Now, which of those two signs should we choose? Well, previously we had chosen this minus alpha 2 solution, right, and I need that to turn into a plus ik2 solution, so I needed to choose the lower sign for I. But mathematically, right, this means that's my choice for alpha 2. Alpha 2 has this value. Now, The last bit is I want you to notice that this comports exactly with this idea of just redoing all of the algebra. Because this relation says then, if I multiply through by I, it also says that I alpha 2 would equal I times minus I k2. Right, here's my minus I k2, multiplying both sides by I, but I times minus I is 1. So once again, I'm left with the idea that I can take the entire previous solution, but everywhere there's an I alpha 2, I can just write it as k2. It's a very powerful concept. I'm going to put a star next to it. You can use it over and over again in quantum mechanics. Now, I should warn you about the one tiny exception to this. Almost all of complex algebra is this will work for. There's just one piece that gets tricky. There's one piece where imaginary numbers and real numbers behave a little bit differently. And that exception is you have to be careful with complex conjugation, with the complex conjugate. Because a real number, right, doesn't flip its sign when you complex conjugate, but an imaginary does. Conjugation. So if you see a complex conjugation, you will want to do some extra special thinking. But either way you cut it now, we can immediately write down our solution to our downward step. I just write out the solution as I had it before, but now making this one key replacement. So, what did we have before? We had integral dk1 with our weights, and notice there's no alpha 2 appearing in here, so everything is still exactly the same. E to the minus sigma squared k1 minus k0 squared, 1 over square root of 2 pi, times then I had e to the I k1x, nothing different there. I'm just copying from memory what we had. Plus, now things get a little different, right? Because I have in the solution, sorry for this, all the panning, right? I've got this fraction k1 minus I alpha 2 over k1 plus I alpha 2. There is an alpha 2 in here. But remember, I alpha 2 I can replace with k2. So it's k1 minus k2 over k1 plus k2. Whoa, that grew on me, right? So it's k, right? I alpha 2 is just k2, so that's k1 minus k2 over k1 plus k2, and that was e to the minus I k1x. That's the solution for x less than 0. When x is greater than or equal to 0, the solution up above, okay, we'll go up one last time, is 2k1 divided by k1 plus I alpha 2. So, okay, fine, I realize that's going to be k1 plus k2 in the denominator. And then my minus alpha 2 we can handle in a moment. So I had twice k1 then over k1 plus k2. Up above, I had e to the minus I alpha 2, but we've been through this before. Minus alpha 2 is plus I k2, so this has just an e to the I k2x. So I've made all of those replacements. And then finally, I have my time-dependent part, which doesn't have any alpha 2s, so it's the same exact thing. There's a factor of I, of course. It's e to the minus I h bar k1 squared on 2m times t. And that is the solution to the downward step.